In case you don't know me, I'm Terri Pigott. I'm actually the Campbell Collaboration Methods co-editor and editor and also co-chair. So today I'm going to talk to you a little bit, give you sort of a conceptual understanding of fixed and random effects models. So let's imagine right now that you've calculated all your effect sizes using David Wilson's wonderful effect size calculator. You have them all ready to go, and now you're ready to do the meta-analysis part of your systematic review. Okay? So, what do we do in a typical statistical analysis? We try to get our means and our standard deviations. We want to look at the distribution of our effect sizes. And so, before you do that, one of the first choices you have to make is this choice about whether or not we're going to choose between fixed or random effects models. So the most common question I get when I teach this, or when it comes up when people are editing, when I'm editing other research syntheses, is, well, how do I make that choice? And what is involved in the choice between random and fixed effect models? Okay. So what we're going to do today is I'm going to sort of give you a description. It's going to be a conceptual description of fixed and random effects models. And I'm also going to give you an idea of what the underlying assumptions are of these two models so that you can make an informed choice about them. I'm going to talk about how you estimate key parameters in those models, and also introduce issues around basic meta-analysis and moderator analyses when you're thinking about using a random effects or mixed effects model. And then I have some resources for you because, of course, in an hour and 15 minutes, you can never cover all the details. So here's the advertisement. Much of my own thinking about this has really been clarified by work of colleagues Bornstein, Hedges, Higgins, and Rothstein. So there's one paper in the journal that David Wilson talked about. And right now this journal is open access until for another year or so. So you can get that from the website. And then also they have an introductory meta-analysis book that's fairly recent that also has much more details about this idea of random effects models and how to make those choices and calculate the parameters for them. So I really encourage you, if this is something you want to pursue, to look at those resources. Okay. We make the choice between fixed and random effects models based on our assumptions of the nature of the variation between the effect sizes in our meta-analysis. Okay. So they both have two different kinds of assumptions about why the effect sizes might differ from each other in our studies. Okay. So we're going to start with the fixed, what I'm going to be calling now, and I'm going to try to train myself to do this, the fixed effect model. Okay. So Bornstein and all adopt this language. Instead of calling it fixed effects with an S, we call it fixed effect. Because in essence, we're assuming that all the effect sizes differ from each other in our meta-analysis because they use different people. There are different participants. So that the only difference between these studies is that they have a different sample of people. So we know that if we are gathering different samples of people, we're not going to get the exact same estimate, say, of the mean of some outcome we're interested in. But what we're assuming in that fixed effect model is that they all are actually estimating a common mean. Okay. So go ahead. So this is a picture I shamelessly stole, whatever we might want to call it, from the Bornstein paper and also from the book. So imagine that if we look at this, we imagine that we're interested in some mean effect size, which I'm going to call theta here. And what we have are two, say, distributions. We see study 1 and study 2. So we see in study 1, I think there's a little flying in thing here. Okay. If we might get that effect size from that study, okay? But the mean of that study the underlying distribution, we were all estimating the same mean. For both of those studies, we see that the only variation, the variation between our estimate of the effect size and whatever that true mean effect size is really only due to the variation, sampling variation in that particular study. So in essence, each study really has the same mean that we're interested in estimating. Okay. So again, this is the same thing. So each effect size from each study is actually estimating some common mean, which is why we call it now a fixed effect model, because there's really only one parameter we're really interested in, well, one in particular, and that is that common mean that each of the studies are estimating. Okay. In a random effects model, we actually assume that there are two components of variation. One is going to be that same one we just saw in the picture before from sampling variation. Every study uses a different sample, so we're going to see some differences across our effect sizes, but we think they're really only due to the fact that we have different samples. The other piece is going to be a random piece, a random variation. This is variation because the effect sizes within each of the studies that we're estimating are actually themselves randomly sampled from some population of effect sizes. So we know that right away they're going to differ. Every effect size that we're estimating from each of our studies are going to differ because the underlying distribution of those effect sizes are all being sampled. The mean is being sampled from an unknown distribution. So our goal in the analysis is going to be to get that underlying distributional mean and variance. So here's the picture. You can't tell this, but the two effect sizes in this picture are really pretty much in the same place as the picture before. But what's different is that we have two different distributions for each study. So they're not estimating they don't have a common underlying mean. But there is a distributional mean that we think is happening. We think that each of those, the means of each of the distributions of our studies are actually sampled from some underlying distribution. And what we really care about then is estimating this underlying distributional mean. So we see we have two components of variation. We have one designated by the V, which is just the sampling distribution for that particular study. And then we have the variation in our underlying population, where the effect sizes, the mean effect sizes are actually being sampled from. We call that's tau squared, the random variance, the variance component. Okay. So we see, again, in the picture, each study, we assume each study is, the underlying mean distribution is being sampled from some hyperpopulation, some population of distributions of effect sizes, and that population distribution has its own mean and variance. Tau squared is the variance. Okay. And again, we have two components of variation. One because every study uses a different population, and one because we're sampling from distribution. Okay. So just to remember, I always have to remember what notation I'm using again. We're using V to indicate the sampling variance for our effect size. So David Wilson this morning, if you were in that session this morning, showed us the importance of that, how to calculate that. Every effect size has a sampling variance that we can calculate. The tau squared, though, is our variance component. This is that underlying variation and the underlying distribution of effect sizes. I'm going to, for right now, call T by our effect size. And that's going to stand for any kind of effect size. This morning we talked about standardized mean differences, odds ratios, and correlations. So they can be any of those. And I'm going to use mu to be that underlying, the mean of the underlying distribution. Okay. So we can, in shorthand form, we can write our two models in this way. So if we have an effect size T, this is for the fixed effect model now. Remember that we were interested in that in the fixed effect model in that common mean, which I called theta. So we have theta there. And each of our estimates of effect size are going to vary from that common mean because of sampling error. And so our error there, our E term, is distributed as normally with a mean of 0. And then there's our sampling variation there, our V sub I. Okay. We can then write our random effects model in this way. So each of our effect sizes, okay, we have our component, our mu, that mean of that underlying distribution. We have E sub I, which is our sampling variation. And then we have that other component, which is that tau squared, that variation from the variation in the underlying distribution of effect sizes. Okay, so each effect size, each estimate of effect size differs from that underlying mean due to two components, one being the sampling variation, one being the random variation tau squared. Okay. Okay, so now given that we've seen what these models look like, the question is, how do we choose? Which model are we going to choose? Because that's going to have implications on how we calculate the mean effect size, how we calculate the variance of our effect sizes, how we calculate estimates of any kind of moderator models. As we said before, that fixed effect model assumes that we only have that sampling error is our only source of variation among our effect sizes. We have some common effect we're going to estimate. This assumption is plausible when our studies are close replications of one another. So when we think that they use the same procedures, the same measures, they're pretty much like replications. The only difference is the sampling variability. So my grad student Josh asked me, well, when would that ever happen? Well, in the social sciences, maybe not. But we can imagine that we have lots of drug studies that are replications of one another. So if we're using the same very strict protocols and procedures, and really the only difference is the sampling of people, then we can see that the variation, that a fixed effect model might be appropriate there. Okay. If you're here, I'm assuming that most of us are social scientists. So that we don't see, and we hardly ever see, exact replications of studies. And we also know that whatever interventions we're interested in are going to be different depending on who's there, who happens to be in the intervention, who's giving the intervention, where the context of the intervention is. We know there's lots of variation. We know there's going to be lots of variation among our studies for all kinds of reasons, and not just because there are different people in each study. Okay. So we often choose random effects models because we anticipate a lot of variation. We just assume that there's going to be lots of variation among our studies. We know that people, even if we're looking at the effectiveness of an intervention, we know people don't implement that intervention in exactly the same way. So we know there's going to be lots of variation, aside from sampling. Okay. So the implications of our choice. As we saw before, we see that intuitively, that random effects model, our effect sizes we're already assuming have more variation than just sampling error. So we're going to have more variation among our effect sizes, more variation among our effect sizes in a random effects model. So David mentioned this briefly, but remember what we do in our meta-analysis is that we use weighted, we weight each study by its precision. Okay. So we weight each study by the variation, by the variance of the actual estimate. So in a random effects model, because we're adding to every variance for every effect size, that variance component, that tau squared, the variances among the sampling, the variance for each estimate of our effect size is going to be more similar to one another than in a fixed effect case. Okay? Because in a fixed effect case, we only have the V sub I. And if you remember from this morning, that heavily depends on sample size. So bigger studies are going to be more heavily weighted than smaller studies. Okay? But if we add then to the variation of each of our effect size variances that tau squared, you can see that what we're doing is making those variances be closer together, look more like each other, have less difference between them. So in other words, in a fixed effects model, we see that we more heavily weight larger studies. But in a random effects model, larger studies are not going to have relatively as much weight as they did in a fixed effect model. So here's an example. This is from the MST. I'm sorry. Oh. This is from the MST study that Julia has done, a systematic review on MST. And these are just 4 studies that I picked out. This is a printout from RevMan. We have our forest plot here. And just to remind you, the little squares, the blue squares, if you can see, are the effect size estimates for each study. The bars coming out of them are the confidence intervals. The size of the squares are proportional to the weight given to each of those effect sizes. So that first one is the biggest study. It has 198 people in it. And you can see that that box is much bigger than the studies below it. And they're actually in order of, and you can, this was intentional, but they're in order of sample size here. Okay. So our smallest study is on the bottom, is the last one. Now, what I've circled there are the weights, the relative weights given to each study when we calculate the overall mean. And the overall mean is the black diamond there. The middle of the black diamond is the mean, and the ends of that diamond are the ends of the confidence interval. This is the fixed effects analysis, the fixed effect analysis. So we see that that biggest study is contributing 53% to that value of the overall mean for the fixed effect analysis. Okay. So we see, yes?
So you're assuming that in all 4 of those studies that the quality of everything else is the same. I mean, weighting it by the number of subjects is certainly one way to weight it, but let's say that the Leishai study, from a methodological perspective, is extremely well done. No, it is extremely poorly done.
Mm-hmm.
And the Henlither study is extremely well done.
Okay.
So why would you weight the Leishai study heavier?
Okay. So I have sort of two ways to answer that. First of all, we do this, we know when we weight by the sample size, we know the distributions of the effect size we're getting. We do this because we know all the distributional assumptions of the effect size. So statistically, that's the right thing to do. Now, but the question of whether or not the quality of the evidence we have is a totally different question. And in that case, what we try to do, because we don't know necessarily how to weight, what the statistical implications would be of weighting by some scale of quality. And by the way, there are 200 plus scales of quality. and we have the methodologists have lots of fights over these scales. But anyway, what we do instead is say, okay, I'm going to code each of my studies. And I'm going to code them for quality, and I am going to check to see if my results differ by the quality of the study. And that's the way we tend to do it, because we don't know statistically what happens when we statistically weight by some quality. Then Julia.
As a follow-up to that, so because you're coding, then do you not exclude to start with? You just take in everything and then code, and then if you find that some are just so awful, whether you code in some value that you skew your data, do you exclude afterwards?
Yeah. Well, you're talking to a statistician. We throw out nothing. We throw out nothing. But right. Yeah. Right. So what I always tell people is that it's much better to be inclusive at the beginning Make sure you code everything you think is important, and then check. Because outliers, like what you're talking about, are going to come up. You're going to see them. And if you really are concerned about the quality of a study, you may look at what your results look like with and without it, and you discuss that in a transparent way. But at the beginning, we don't want to exclude anything because we really want, because our goal in a systematic review is to actually get a picture of what that literature looks like, good and bad. Julia? Yeah.
Yeah, as it turns out, in this picture, these studies, you see the numbers over to the left, 01, 04, those are study quality rankings, as it turns out, based on other criteria. So we're reporting, so much like is the most rigorous study and is the worst in this pile. But as Terry suggested, we don't want to use weights algebraically to adjust the effect size based on study quality ranking and affecting a lot of different things. So what you can do is put them in order as design on the slide.
And you go ahead.
Yeah, but to say you don't want to use study quality to do weights because there's something mathematical dangerous about that, why wouldn't that apply to sample size as well? I mean, weighting it by sample size is such, I mean, sample size is such an arbitrary variable for importance. I mean, I've seen lots of very large, very poor studies and some very small, very good studies.
Right.
It is interesting that it
Yeah.
correlates perfectly in this particular case.
Of course it does, yeah.
But,
Right. But that's absolutely true. But statistically, these effect sizes, the variance of these effect sizes, the way their distribution is based on part on the sample size. So, yeah. So this, again, is the fixed effect version of this, okay? So, the next slide. Here's our random effects version. So look at, first of all, if we look at our forest plot, there's a couple things we notice, right? Now, granted, I made a copy of this, so it might be, there's always some problems with sort of the visual, but the boxes are relatively equal. We don't see the big box on the Leischeid study. Are you trying to, what are you doing, Josh? And we also see, right, our diamond is much more stretched out. So we have much more uncertainty in the random effects model. We're incorporating much more uncertainty in the random effects model than we do in the fixed effect model. And if you look at the weights, they're very close together. That doesn't preclude us from also, I mean, in a random effects, we still would want to look at issues of study quality, of different things that might be going on in the variation across the effect sizes. It's just when we calculate the mean effect, we are weighting the studies a little more equally because we think there's there's more uncertainty there than just what's due to sampling error. Everyone see that? Okay. Okay, so where are we so far? So we've talked about the underlying assumptions of fixed effect and random effects model, talked a little bit about the reasons why we would choose between them. So now I want to talk a little bit about the basic analysis that we do in a meta-analysis and a little more detail about moderator analyses, especially in the case of random effects models. Okay. Okay. So in sort of our first thing we do in a basic meta-analysis is we're interested in estimating our common effect and its standard error. So in a fixed effect model, we're going to be looking for that theta. We're going to calculate our theta. We calculate that by using we get a weighted mean of our effect sizes using that fixed effect weight. That fixed effect weight is mostly dependent on sample size. We get its standard error. We also want to know how much heterogeneity there might be among our effect sizes. We calculate the statistic Q. Okay? What we will not do, we will not decide on the basis of a significant Q that, oops, I made the wrong choice, I'm going back to random effects. Okay? We will not do that. What we will decide is ahead of time, on the basis of our substantive knowledge of the of what we're looking at, of the area of our review, whether or not we think studies are going to have a fair amount of variation. Okay, and I emphasize this again a lot because I think that there's lots of decisions we're going to make in a systematic review that are absolutely dependent on our substantive knowledge of that area of the review. And this is just one more example of how you really need to think ahead of time, a priori, about what these studies are going to look like. How varied is this area that I'm looking at? Are people pretty much doing the same thing? We're all using the Beck's depression inventory. We're doing the same kinds of procedures, blah, blah, blah. Or are we using all different kinds of measures of depression? Do we have all different kinds of interventions sort of mixed in with different components? How much variation do we think is really going to be in these studies? And that's why people tend to now choose random effects models. 10, 15 years ago, if you look at older meta-analyses, you'll see people using fixed effect models. But now I see people say a lot of the time, you know what, these studies are so varied. They vary more than just by the fact that there's different participants. We think that there's a lot of underlying variation. We're going to use a random effects model. And that does give us a little bit more conservative estimates as well, as we saw. Okay. Now, in a random effects model, we're also going to get a mean and some variation. But in this case, we're actually trying to estimate that mu, that underlying mean of the underlying distribution of our effect sizes and our tau squared. And we're going to test heterogeneity by testing whether or not our tau squared is different from 0. Okay, so if you remember that picture, the picture of the random effects model, if we have no variation in that distribution at the bottom, then we're back into the fixed effect sort of case. Okay. But our biggest difficulty is how do we estimate tau squared? Okay. So there are two main methods for computing tau squared. The first one is variously called the D'Ursimonian-Laird estimate, which is based on a paper D'Ursimonian and Laird did on meta-analysis, and I can't even remember when it was, in the 80s maybe, yeah. It's also called the method of moments, and we also then, the second one we have is restricted maximum likelihood. The method of moments estimator is easy to compute. It's based on the value of Q, the homogeneity statistic. You don't need anything other than a calculator to do it. And in fact, every package program that does meta-analysis will give you that. And David Wilson, by the way, did not tell you that he's not a good enough, promoter of himself. He had on his website and I think you can link to his website from the Campbell website, is a set of programs to do meta-analysis in Stata and in SPSS. Okay, so that code is there, and you get all this stuff out of. If you don't have access to things like comprehensive meta-analysis, or you don't know R has a set of programs, right? Yeah. Then you can get the homogeneity, you can get the Q and all the other things you need that are in his book, which, by the way, is very good, from his website. Okay. So most people report that Q based on the method of moments. The restricted maximum likelihood is more difficult because it requires an iterative solution. Okay. But this is the method of moments estimator. You can see it's based on Q, which is our homogeneity test. It's also based on K, the number of studies we have, the number of effect sizes we have in our meta-analysis, and it's also based on this thing called C. And if you look at C there, it's some combination of the weights, and these are the fixed effect weights. Okay, so it's based on the variances of each of our individual effect sizes. And again, this is the estimator used in many meta-analysis programs, such as RevMan and comprehensive meta-analysis, because it has a closed form solution. It's easy to compute. Okay. But many statisticians don't like the method of moments estimator. I know, my life is so exciting. Spend a lot of time, arguing with people about, the Dersimoני and Laird estimate versus some other estimate. But we can estimate that tau squared using HLM, SAS-Proc mixed, or R. I can give you those programs. They're more stable estimates. They're more conservative estimates as well. In the handbook in the second edition of the Handbook of Research Synthesis and Meta-Analysis, that's edited by Cooper, Hedges, and Valentine, there's a chapter in there by Steve Rodenbush that actually compares the different estimators of tau squared and comes to the conclusion that the restricted maximum likelihood one is the one. But again, it requires a little more work on your part to get that. And most people just report the method of moments estimator. That's not, there's no one, no one's going to fault you for doing that one. So that's sort of common, okay. Okay, we're okay so far. Okay, so remember we need that tau squared in order to, so we're going to need our estimate of that tau squared so that we can get the correct weights in order to do our meta-analysis. We need that tau squared so that we have the correct weights for each of our effect sizes so that we can get the correct mean effect size that's weighted by the random effects variance, which is our sampling variance plus tau squared. And we're going to need it for any other analyses that we're going to do. Okay. Because the fun part, or one of the more exciting parts, I know, really my life is not that interesting, right? Okay. Of meta-analysis is actually doing those moderator analyses. Once we have our set of effect sizes, we usually do a synthesis because we think that there is a lot of variation among our studies, and we have some ideas a priori about why. We're doing this synthesis because we think we have some theory about that underlying set of studies or the intervention or whatever phenomenon we're interested in, and that we've spent all this time extracting the data from the studies. And anyone who's done a synthesis knows that the majority of the time spent in doing a synthesis is not in the statistical analysis. It's all in the front end. It's all in the deciding on the question, and gathering the studies, and extracting data from the studies. Okay, so we've done this because we really want to see what might be related to variation in the effect sizes. We've extracted all this information. We have some logic model based on some substantive knowledge of the area, and we want to see how the variation in our effect sizes relates to the differences in the methods, procedures, measures, whatever it might be in our synthesis. Okay. So let's suppose that we've decided that we're going to use a random effects model, okay, and we've gathered a bunch of studies, and we think in a very simple way, well, maybe our effect sizes are going to differ depending on what age of the kids are in our particular study. So let's say that we have a moderator now that says we want to group our studies, our effect sizes, by whether or not the kids in each of the groups are mostly elementary school, middle school, or high school kids. Okay, so we have this simple moderator, which is grade of the children. Okay. So we have our three categories: elementary, middle school, high school. It's a categorical. We're going to treat it as a categorical factor. So we're going to do something like a one-way analysis of variance, an analog to one-way analysis of variance with our effect sizes. And in that analysis, we're going to do what we normally do. We want to know what the difference is, if there are significant differences in those group means. Okay? That's what we do in analysis of variance. We do the same thing in a meta-analysis. We want to know if the mean effect size within each of those groups is different from one another. The question is, how do we calculate the mean within each of those groups? What assumptions do we make about tau squared? Okay. So in this case, we have sort of two options. So what we've been talking about all along so far is that we only have one tau squared. All of our studies are estimating effect size coming from the same distribution. We have one tau squared. And so we're only interested in estimating that one tau squared. We might make the assumption, pardon me? Oh, is there a question? Sorry. Okay. We might make the assumption that each of our groups actually comes from a separate distribution. So each of our group of effect sizes may have its own underlying mean and variance component. So that we really need to estimate the mu for the elementary school group, the mu for the middle school group, the mu for the high school group, along with their underlying variance components. So this would be sort of what sometimes people call fully random effect, okay, effects model. The problem is that we usually don't have that many studies. If we have a small number of studies within each group, our estimate of each of all these different variance components is really going to be not very precise. And it doesn't matter how we estimate the variance component. If we only have a handful of studies in each group, we are really on shaky ground estimating variance components within each of those groups. Okay? So we usually do option 2, which is that we do what we've been doing up until now in this presentation. We assume one variance component across all studies, and we use that variance component in all of our calculations from there. Okay? So we estimate that variance component at the beginning of our meta-analysis. We calculate our overall mean and the variance of our overall mean estimate. We also then calculate our group means on the basis of that single variance estimate. Okay. And this also applies to if we're going to do a meta-regression model. So we probably want to estimate that single variance component when we're going to do a meta-regression model. Okay. So we also do, just as an aside, we use regression methods as well in our moderator analyses when we want to look at more than one predictor at a time. And when we do has been now called meta-regression in the meta-analysis area, we have to use weighted least squares methods, and our weight in a random effects model is going to depend on that tau squared that we estimate. Okay. So this is just a little example from that I have just to sort of highlight the points. This is sort of data from a meta-analysis of studies that look at the relationship between socioeconomic status and academic achievement. And the goal of this particular synthesis was to look to see if the strength of that relationship between socioeconomic status and achievement depends on how either of those two things were measured. So we know that in the United States we have millions of ways that people measure socioeconomic status: income, mother's education, father's education, status of the occupation, and so forth. And we also know that we have lots of ways of measuring achievement. In this particular little moderator analysis, I was comparing what the relationship between all types of SES measures and achievement were like by separating out the studies by whether or not the academic achievement measure used was a state test. So a test developed by a state, like I know Massachusetts has one, Michigan has one. They have their own state tests, or whether it was some standardized test like the SAT or the ACT. Okay, so in this case, these are random effects means, and the standard deviation of that mean effect size is calculated from the random effects, but it's calculated from a single estimate of tau squared. Because look at how many studies I have in each group. I don't think I'm going to, with 5 or 6 studies, I'm not going to get a good estimate of tau squared within each group. I'm not going to risk that. Instead, I'm just going to assume that I have used a common variance component across this particular analysis. Does that make sense? Okay. And as an aside, we can see that the state tests come up with, these are correlations of these are weighted mean correlations, just as a substantive background. We can see that it's the much stronger relationship between state tests and academic achievement than between standardized tests. Okay. Okay, so some concluding remarks. I think, as I said before, and as I think that many of you, I saw lots of heads shaking, usually in the context that we are all working in, the random effects model is probably the right choice. It's more conservative, it reflects better the assumptions we make about our studies and the effect sizes we're getting from our studies, that there's lots of variation among them, and some of it we may never know why. Okay. And then so from the C2 methods editor, if you're going to send something to Campbell, make sure you provide a rationale for your choice in the protocol, a priori, before we start doing analyses, based on some substantive reason you have. It doesn't have to be a statistical reason. In fact, I would rather see a substantive reason. Why do you think these studies are going to vary so much? Because that also clues me into what your underlying theories are about what's going on in this set of data. What's going on in this literature base. So that's my little plug for Campbell. And then the next slide gives you a few more references that are useful for the whole random fixed effects things. The Bornstein, here's the Rodenbush chapter in the Handbook of Research Synthesis and Meta-Analysis, and then a reference for the example I showed you. So that is actually all I want to say to you. So